So let's practice some naming. So we'll start very simple. So the first thing we have to do when we're naming is we look at the functional groups present. And the functional group present here is alkane, since there are nothing but carbon-to-carbon single bonds. And of course it is understood that hydrogens would be surrounding all of those carbons, and they would all have an octet. We're leaving all that off. So since alkane is the functional group, the suffix will be ane. Now we find the longest chain of carbons containing the functional group. And in this case, the longest chain of carbons is 4. The prefix for that is but. We combine those two, butane. Very simple. Agreed? Okay. So let's get a little more complicated because that was laughably easy. When there are functional groups attached, we have to make sure that we indicate the location of the functional group with a number. Only necessary if that functional group could be attached elsewhere. So for example, that compound is an aldehyde. This is identifiable as aldehyde. This would be R in our generic symbolism up here. Okay? So the suffix is going to be al. There are 1, 2, 3, 4 carbons, and yes, we count this carbon. There are 4 carbons long, so it's but as a prefix. The an is not important where it comes from, so I write butanal, not ol. That's an a. I know it doesn't look like an a perfectly. Do I need to put 1 butanal here? No. And the reason I don't here is I cannot write this group anywhere but on the ends. If I had it on this end, it would still be butanal. It wouldn't be 4-butanal because we start numbering from the side closest to the groups. Aldehydes are termination groups. Acids, termination groups, so they have to be on the end. If, however, that compound on the end was not, or the end was not an aldehyde group, say it was this, that's a different story. This is an alcohol, so it's not butanal, it's butanol. But I need to indicate where the alcohol is attached because it would be different if the OH was attached here. That's a different compound. So this compound is known as 1-butanol. If the OH were where I scribbled this one out, that would be 2-butanol. Suppose the OH was here. That would be 3-butanol, correct? Of course not. We start numbering from the end closest, so that would also be 2. Okay? And that's a good lesson in how this works. You have to be able to, in organic chem, if you're really going to want to try and excel here, you have to understand this is 3-dimensional space. So if you pick this up off the screen and you rotated this end over the top to this end, it would basically put that OH here. It would no longer be here. And that black OH on the other side would be attached over there. I should have reversed those, but you get the idea. It's the same compound. It looks different, but it's the same. Okay? Any questions on that? Anybody feel they need more practice naming? Nobody? Okay. Then I want to go ahead and move forward. I want to get to some new material. So what you'll see on this page, I've taken that link at the top is just, I'm going to show it. This is for the video. You don't need to write that. That is the link for the chem guide, which I showed you guys in class yesterday. It shows all the things you need to know for the IB test. The reason I'm doing that is because we are studying topic 10 right now, and so I've included some headings for those people who want to study. They can cross-reference. Okay? So the first thing we're going to talk about is what a homologous series is. And so with a homologous series, you have to understand, first of all, what it is. A homologous series, by definition, a series of compounds with same functional group that differ by one CH group. Okay, so in other words, long story short, it's a series of compounds all with the same functional group. They only differ in carbon number. That's it. So as an example of a homologous series, I'll just start with the most simple. There's methane. The next in series is ethane. Notice they only differ in one carbon. The next in series would be propane. I'll leave the H's off for simplicity. The next in series would be butane. The next in series would be pentane. Do I need to continue? It's very simple. Now, it doesn't have to be just alkanes. We could do the same thing with alcohols. Methanol, ethanol, propanol, butanol, pentanol. With aldehydes, there is no, well, you could have methanol. Methanol, ethanol, propanol, butanol, pentanol. We could do the same thing with any of the functional groups. A homologous series is simply the same thing with one extra carbon. Okay? You guys all good with that? Now the reason you need to know that is not simply to define what homologous series is, but rather to understand the physical properties of chemicals in a homologous series. So remember, physical properties are typically a function of intermolecular forces. I'll show you this picture that I just kind of briefly showed there in a second. But some examples of physical properties: melting points, boiling points, volatility. Does it evaporate very quickly? You're going to need to know about those. And those simply rely upon one thing, and that is intermolecular forces. So something that has very strong intermolecular forces will have a very high boiling point. Something that has very low intermolecular forces will have a very low boiling point. It's a very simple concept. You guys have a question about that? Are we awake out there? I'm going to ask that on the video too. You got to answer when you get to the video. Okay, so good. So let's think this through. Now there are three types of intermolecular forces. We have hydrogen bonding. We have dipole-dipole forces, which I'll abbreviate DD, and we called the third one London dispersion. You're going to notice in that chem guide with the link at the top, they call those van der Waals forces. They are exactly the same thing. So when you read the phrase van der Waals, that's a London dispersion force. It means exactly the same thing. So remember, please remember, these two are polar intermolecular forces. They come about because of unequal sharing of electrons. A hydrogen bond is a special category where hydrogen is attached to a very electronegative element, either nitrogen, oxygen, or fluorine. Dipole-dipole forces are present when the bond is polar and the molecule is not symmetrical, does not cancel in space. Okay? London dispersion forces are present always. They only really show their head, however, when none of the other two are present, as in our homologous series here to the left. So let's think this through. These show only van der Waals forces. Agreed? Carbon to hydrogen, nonpolar bond. Carbon to carbon, nonpolar bond. So all the bonds here are nonpolar. And they all have a tetrahedral arrangement around each carbon. They're all symmetrical. There are no unshared pairs. There is no polarity. These are nonpolar compounds. So the only force is van der Waals, intermolecular forces. And intermolecular forces, more specifically, van der Waals forces, depend only on one thing: the number of electrons. Van der Waals forces are instantaneous dipoles created by the motion of electrons. And if those electrons find themselves in one location just for a microsecond, for an instant in time, that creates a very small, very weak, very quickly dissipated, the word is instantaneous, dipole, which influences its neighbor to also form an instantaneous dipole. Now that's something we haven't discussed in quite a while. Does anybody have a question about that? Okay. If you do, you can see me right after this part of the lecture and we can go through it. But just understand that they are temporary and fairly weak individually. But when there's a lot of electrons, those little tiny forces, millions of times over, add up to fairly significant forces. So the only thing here are the van der Waals forces. And if they are dependent upon number of electrons primarily, which in this series, from this one being number 1 to this one being number 5, which in that series has more electrons in it? 5. And therefore, which in this series has greater intermolecular forces, London dispersion type? Number 5. So, if that one has the stronger intermolecular forces, it should have the highest boiling point. This one should have the lowest boiling point, or melting points, any of those physical change properties. Agreed? Very simple. How about this question? Which in this series will be the most volatile? Volatile means evaporative. Which one will evaporate the easiest? The first one. Why? Weakest intermolecular forces. Do you understand how that works? It's a very simple concept. So you need to understand what a homologous series is. Check. It's a sequence of compounds who differ only in number of carbons. Number two, you need to understand how their physical properties change. And remember, that's a function of intermolecular forces. In the case of these alkanes, more chemicals, stronger forces, higher boiling points, higher freezing points, whatever the case may be. You guys all okay with that? Yeah, Fabio.
So would 5 also have the highest freezing point?
Say it one more time.
5, does that also have the highest?
Yes. The phase change point, the temperature, if the forces are strongest, there'll always be a higher value. Stronger means higher. Okay? Always. Okay. Now, please understand, in addition, that it doesn't need to only apply to alkanes. It could also apply to, say, alcohols. So if I add these OH groups to the end, these now all become alcohols. This one is ethanol. I do not need to number it. This is 1 propanol. This is 1 butanol. This is 1 pentanol. So now, let's talk about this. What primarily determines, in this case, what is going to determine the strength of the intermolecular forces here? How about this? Is it going to be hydrogen bonding? Is hydrogen bonding going to differentiate between the chemicals in this homologous series? The answer is no. The reason the answer is no is because they all have hydrogen bonding. That does not differentiate them at all. So in this case, in all homologous series, the only difference is number of carbons. So which of these has the stronger intermolecular forces? Number 5. It has hydrogen bonding, as they all do, plus the additional number of carbons. Okay? Now, we have to be very careful about this, however, because it's easy for us to just fall into this trap that more carbons means more everything. Okay, that's not necessarily the case. It does mean stronger intermolecular forces. That is correct. But there are differences. Okay? So let me go ahead and pause this video. I'm actually going to stop it.